My name's Richard Soden. I'm the Space and Satellite Application Lead at Keysight and a confirmed Space Geek. In this series of webcasts, I'll be joined by my fellow Space Geeks, Mark Lombardi and Ian Furness. Mark has over 25 years of experience in power, time, and frequency domain measurements. Used to work specifically on supporting satellite and modem developers, and he and I have been working together for the last 5 to 6 years, specifically on Keysight's space and satellite business. Ian is relatively new to Keysight and to test and measurement. Used to be an electrical contractor and had his own business. When he's not working on space and satellite business, he's getting his kids excited about science and engineering. Today, we are very happy to be joined by John Swanstrom, our colleague who's based out of our Santa Rosa offices. John has been working on the design and test of antennas for how many years, John?
I'm going on my 46th year right now.
Okay. So, despite his face, he's what we would call a grey beard. He actually developed the switched beam quad antennas on the space shuttle that were the primary communication links to the ground stations. And he's also worked on some of the GPS satellite antennas as well. So we could probably spend a few hours discussing just those two projects. He graduated from the University of Illinois, and before his time at Keysight, Agilent, and before that HP, he went to work at Rockwell International in Southern California, where apart from learning to surf, he worked in their antenna design, development, and testing group. And as I say, we could probably do 2 or 3 hours talking to John, but today we're going to talk about antennas and steerable antennas. So to kick this off, John, why do we need steerable antennas for space and satellite communication?
Yes, well, thank you, Richard. So steerable antennas are necessary for a variety of reasons. If you have a geostationary satellite, occasionally you'll want to switch where you're putting the energy onto the ground, say from the East Coast to the West Coast, so moving some demand. But more importantly these days are these low Earth orbit satellites that actually process across the sky from one horizon across the top of the overhead and then disappear on the other horizon. And they need to steer their energy, and also the ground stations need to track them also. And we have a short video that kind of illustrates this as to how the antenna patterns have to move as the satellite's moving. And we'll take a look at that now. And Mark Lombardi will tell us a little bit about this.
There we go.
Here it is. Yep. So this is a relationship we have with AGI and STK. It'll show the flyover and our connection with our system view software. You'll see here we have an animation in AGI's SDK of a LEO satellite flying over with a phased array antenna. So all that information about the Doppler shift and the delays are getting fed into a simulation where you can now generate the waveforms and actually have them not only in a full end-to-end simulation with not only just the electrical properties, but also the kinematic properties. And you see here our VSA software actually demodulating the communication signal through that animated system. So the real key here is the dynamic nature of these LEO satellites, and then on top of that, the dynamic nature of steering phased array antennas. And so it's great to have John available for us to talk a little bit about the challenges there.
Hey, can I just say real fast, a shameless plug, that the simulation software that was in there was our Pathwave system design, formerly known as System View, so mixed with AGI's STK software.
Thanks, Ian.
Yeah. Well, thank you, Mark. That kind of illustrates why steerable antennas are so important. And of course, going way back, they used to be mechanically steered, but the ability to electronically steer an antenna is very desirable. They're lower weight and they're much more reliable. So my first phased array antenna was 2 elements, as Richard talked about, for the space shuttle, and it would steer the beam to the left or to the right as the satellite processed, as the spacecraft processed overhead. And over the past 40 years, phased array antennas have gotten a lot more sophisticated, a lot more capable, and a lot higher performance. I've had the opportunity to talk to a lot of customers that are developing phased array antennas in my career here, and I talked to them about their workflows. And of course, the workflows have become much more complex as you design these higher complex antennas. But fortunately, the tools that we have available have also increased. So as we saw with the software that Mark talked about, there is some design software that's used by many people. And in talking to most customers, I ask them about their workflow and I say, how much of your time is, where do you allocate your different resources? And I was amazed to hear that about 60% of their design and development efforts is in simulations. And so they use different types of software to help them simulate all different phases of it, because these phased array antennas are very complex and you don't want to go through a lot of prototype hardware trial and error. So if you want to have a real high confidence that your first prototype is very close to being the right one. And this Pathwave system design software has been very useful for that. Very easy to use. It's very fast in simulations. It is very accurate models. It's been fine-tuned, and you can do just amazing simulations with it to get to very close to knowing what your phased array will do. So it's very accurate modeling, and you can use a variety of things. You can use for different components in your phased array. You can use circuit models. You can measure the S parameters. You can measure the X parameters. You can take customers' data or suppliers' data sheets and use that data, plug it into the model, and do very good simulations. As you start to develop elements, say an element of a TR module, you can actually measure its S parameters, plug that into the simulation. So that works really well. So we've seen a lot of emphasis on simulations, moving away from hardware.
One of the things I think that is also useful is, as you say, is that notion of using S parameters, and as you say, you can take that from a data sheet, or you can actually measure it and then import those characteristics into your model, and then make a better model, and then improve your model and build that out before you were actually even have hardware, right? You could start with the actual component parts and actually do trade-offs as well and things like this, and sort of work out what the parameters are and build out your design within the simulation, and do a lot of debug. And that whole notion of digital twinning, right? You can the whole notion of doing the AGI STK interface for the actual orbital parameters. You can actually fly your simulation and do everything within the simulated in a software environment. So
yes,
there's a lot of de-risking involved, right?
There is. Yeah. It's all about de-risking. If you look at, when you build a two-element phased array antenna, there's not a whole lot of risk in it. It switches to one position to the other position. These newer ones that have been developed, very complex, very capable, but there's a lot of risk in this, and the software simulations really de-risk that. And everyone that's building phased array antennas realizes that, and they're using simulation software. And like you say, many different simulations. Certainly tolerances are important. So they do some Monte Carlo analysis to say, well, we get a little bit of variation in all of our different components. How does that affect the final performance? And these really high performance phased array antennas that are all areas of our life, but especially in space, that we're seeing up there are the result of these simulations. And it'll be a very interesting topic that you'll cover in the future session. And for anyone involved in phased array antennas, you'll be very interested in that, and the assurance that you're going to have a successful design in a reasonable time period and a reasonable cost is a result of these great simulations. Well, next I'd like to move on. Yeah, go ahead.
I was just going to add, one of the things that really surprised me is all the interdependencies, just from very simple things like the choice of what, are you using a 5-bit DAC or a 6-bit DAC to control the phases, or are you, what's the frequencies you want to cover? Because when I first learned about phased arrays, I thought of them as simple, kind of just you just simply steer things. But you realize, oh, wait a minute, that phase has frequency dependency, and that frequency dependency is impacted by a lot of different things, especially in these complex mixed signal systems. They're not only analog systems, they're also digital systems.
Yes, yeah, they are, and they're very common. And it's a system design too. It's not just the antenna anymore; it's the overall system and the noise performance of the overall system and how all the different components add to that. And the only way that I know you can do this with these complex systems is through these simulation models. They can do, just lots and lots of calculations very quickly and come up with very good statistical analysis as to how the systems will perform. So that'll be a very interesting topic to explore further